Hey, how's it going, guys? So here we are back again. More of the optimal start mathematics playground. So we're studying mechanical engineering theory with Python and some of the math models defined in research. Look in the PNNL paper directory. That's the Pacific Northwest National Labs that came up with quite a few different mathematical models that output minutes to warm up or cool down the zone. So basically, the buildings, when they're unoccupied in the winter, the zones get cold, or in the summer, the zones get hot when the HVAC isn't running. And these different mathematical models output minutes to warm up or cool the zone. So we've been talking about this a lot. We capture for these models zone temperature and an occupied set point deviation. That's the delta temperature. Some of the models have outside air temperature factored in. So this is like a little bit of some about the models, where they're described. We did model 0, which is just a linear degree per minute type of model. This actually runs in the building automation system, comes with the manufacturer that I use for building automation. And then there's also a model 1, which is more of these fancier models. We covered this already, quadratic model. It's just delta temperature, uses quadratic regression, some closed form mathematics where the regression model gets fit every time you run and update the model. This is model 2, which is also the model 0 plus this weather ratio. So it factors in weather data, outside air temperature. I'm also getting some really good results when I'm, which I've also shown you before in other videos, vibe coding Java. Model 2 is actually working, it appears to be the best. But the research paper showed Model 3 got the best performance. And Model 3 is a linear regression, multiple linear regression type model that uses delta temperature, outside air temperature, some other variables that account for the lag of the building's thermal lag. The last set of bonus videos to this says we did all the matrix algebra by hand. And then now we're on to model 4 on bonus day 10. So this was the first order response physics driven model. I'm learning a ton here. I actually don't remember any of this stuff in my undergraduate, my undergraduate program, which I graduated 20 years ago already. So yeah, first order, where it's an iterative model when it's fit, and there's some log math that goes in solving for basically minutes that the required to condition the zone. So little description. Okay, so we're in bonus day 10 of the content because I had to add some more bonus days because I think our AI generated coursework wasn't in depth enough for me. So maybe some of the younger audience that are fresh out of engineering school, they might be able to say it's easy enough, but not for me. So okay, so we're studying model 4 a little bit more in depth like we did on model 3, but we're studying some of the math that you could run manually behind the scenes. So let's get into it. So the past 2 days, that was first order intuition, and the one we did the other day was exponentials and logs. So here we are on day 10. We talked about deadband. All right, here we go. So goal is to understand deadband and why Model 4 needs it. In the paper, Model 4 uses a constant parameter representing an acceptable deadband from set point. A thermostat rarely targets the exact number. So we talked about this the other day. I think that we, in our code base, forgot to bring this up. Let's see, where were we? So we're in here. Sorry. Wrong directory. So optimal start math playground. Here's our math lesson script. Put you in the right window. Set VS Code up. Some of the really early videos we went through in setting up Python for some of these exercises. So we kind of talked about the last video, degrees Fahrenheit, where I am at 72 is typical temperature set point for a zone. And if we have a deadband of 1, that would be a half a degree up and down. So like the effective heat would be 71.5 and effective cool would be 72.5, which is, that would be an unusually short deadband. Typically what we see is a deadband of 4 degrees. I'm in degrees Fahrenheit. So like 2 degrees up and down. In the United States, there's actually energy code requirements. So code requires 5 degrees, so the engineers always design to code. And then the building automation people just kind of set up whatever they feel like it. So they usually do 3 or 4. I rarely ever see 5. It's better for energy efficiency if you have a bigger deadband, but it could get into the scenarios where the control system doesn't respond fast enough and people could complain, I guess. So the basically I think like what this is trying to say, like this algorithm for whatever reason needs a deadband. I use it in the Java code that I've vibe coded to. I called it a temp tolerance, that the temperature has to get within a certain tolerance of set point, and it's pretty much the same thing as deadband, I guess. But let's see what we got for our math lesson here. Okay, so we have another one of these tiny math lessons. So I might just go comment all this stuff out. This is our previous lessons. Python, you just use a comment with quotes, or you can use double quotes. So anything in between 3 quotes is basically commented out of the program. Some other languages use forward slashes like C, C++ or Java, but Python is quotes, and also a hashtag for single line comments like that. Okay, so if we do a Python math lesson okay, so I think I have to go one directory in. We might have to go inside the lessons directory. Okay, so now we can't find it. Oh, I know what we need to do. So if we go back one directory, I think I just need to put this lessons. There we go. So the coursework is in this directory, which is also has another directory. This scripts. AI came up with all this stuff, so it's kind of cool. But this is just some little helper scripts that AI came up with to create our lessons. You can also see that on GitHub too. So here we go in our math lesson for today. So this is a for loop for 0.5.25 model 4 optimal start. Their looks like they're feeding in. So they're feeding it, so like they're looping through these deadbands. I wish they would just call this like deadband for deadband. In here, we pass that into whatever little helper thing the AI created. So that's how we come up. So that's how it's coming up with this. So basically, it's just some simulated code that's just saying the shorter the deadband, the more minutes that your control system probably has to run, which makes sense. That's why for energy use cases, I think that the wider the deadband, the less time you have to use mechanical cooling, electrical energy on fans or chillers or boilers to get to your set point. So if our deadband is really small, the HVAC system just could take more minutes to achieve that temperature set point. Hopefully that makes sense. If your site complains about late to set point, do you make the deadband bigger or smaller? Usually people in the real world would not complain that the building is late to set point. They would just complain that the building is cold or hot and they're unhappy, and then the controls technician has to decipher the data or watch it in the live system and then determine that it is maybe slow to set point, I guess. That's like a really weird way of doing it. So usually that would mean that you would make your deadband late to set point. It does not make any sense to me. Usually people would complain that they're either too hot or too cold, and the controls technician wants the building to respond quicker, so they'll tighten the deadband to force more cooling, more heat, whatever they need. So usually you make your deadband smaller to improve the way how fast the system responds. And then if you want to save energy, you widen your deadband. If your site complains that it starts too early, which the real world would never do that, what deadband might you change? When we ran the code, the wider the deadband, less minutes. Why is deadband a policy decision and not just math? I have to ask that. That's almost like getting into like machine learning language. Let's see what ChatGPT has to say on this. So we're on bonus day 10. What does this mean? What does this mean? It sounds like machine learning language. Deadband in optimal start would indicate how long the algorithm needs to run as a policy. I don't know. Seems kind of like a weird question. Short answer. Deadband is a policy decision because it defines when you choose to stop caring, not what physics requires. Math can tell you how fast a building converges. Deadband tells the algorithm when, it's good enough. That makes sense. So, of course. So, like when I was using temp tolerance in the vibe coding, the Java, and all these optimal start, when the temperature reaches a certain tolerance of the zone temp and set point, it's good enough. So I guess that in terms of policy, or yeah, I guess that makes sense. Okay, so key deadband is where comfort policy meets runtime math. All right, so maybe we could try another one here. Bonus day 11. This is bonus day 11. It's wrong right here. Estimating the C parameter from real data. Estimate the first order decay ratio from a batch of error samples on startup. If your error sequence after startup is E123, your first order behavior is like E is approximately C times E0, E2 is approximate C times E1, I guess. So C is basically a typical ratio of the consecutive two errors. Seems kind of cool. This matches the structure in equation 23 in discrete form in the paper. So tiny helpers. More tiny helpers. Guess we could even just do this. So I'll just use in our Python here comment out that line. So what do we got here? Well, I can't see like what it's actually doing here, but errors. So it's passing in this list of errors to this function. So if we went and looked at that function, here, I guess. What the heck? Anyways, I thought it would be kind of nice to look at estimate C least squares. So this is actually the code that it's using. Maybe we could just actually, whoops, I'll just copy this and just say blast away our other stuff and put our function right in here. And then we don't even need to import anything. So see what this algorithm looks like. So this is like the math that's going on behind the scenes. So it's actually it's looping through this data structure here. These are our errors, I guess. So it's just computing the previous error, current error, and then this is computing a ratio. How do you think about that? So yeah, so it makes sense. So that is our ratio, our C parameter ratio in our equation. This makes me just want to look back on here real quick. I might just go back to what was C again? So, okay, so C, alpha C. C is the dynamic system response factor, continuously updating using least squares learning from historical recovery curves. Cool. B is initial temperature difference between zone and temp point, and A is acceptable temperature tolerance. Deadband. So we take the log of these two divided by the C parameter, dynamic systems response. Wow, that's really interesting. So it's pretty cool. The people that come up with these mathematical models and research they're PhD engineers, I think, most definitely. So it's kind of cool. It's really neat for me to learn this stuff. Okay, so where were we? So we were just looking at our equation. So interpretation, C hat. Near 0.95 indicates a strong system, fast improvement. When C hat is near 0.97, weak system, slow improvement. Try the same errors but add noise, jitter. Okay, so if we added some noise, that's making really odd. Maybe add in a really slow one here. And then how about just a normal looking one here. Whoa, and yeah, that significantly causes our C parameter to be quite a bit different. So that would a lower parameter, at least according to our lesson plan. Strong system, fast improvement. All right, does the estimate stay reasonable? I would say no. Try an example where errors stop improving. What does C hat become? So where errors stop improving. So maybe if we just did, I think there would be like if we did, let's see. We just have to simulate this. And we would just do probably like the same data or something really close in each run. So I'm just making it really kind of similar to these other numbers and just see what happens. So that really makes it bump up to almost a value of 1. So I guess that means weak system, slow improvement. Makes sense, I guess. That's kind of cool. So model 4 learned strength from the trend of air decay, not from a single shape or single slope. So cool. Well, we got two more of these models checked off the list, and I'll keep on having to show you guys some updated screenshots of like what I'm running in the field and the program objects, and we can see some of this more in real time. So until then, thanks for following along. Talk to you tomorrow.